Innovate to sustain.
What if everything you are, your thoughts, your curiosity, your very consciousness, is not separate from the universe but a continuation of it? What if the same forces that forged stars, shaped galaxies, and scattered the chemistry of life across space are now thinking through you? From the first human who looked up at the night sky to the missions that now leave Earth behind and reach into deep space, this is not just a story of exploration. This is the story of how a universe slowly became aware of itself and how we are only at the beginning. Long before equations existed, humanity's relationships with space began as perceptions. Ancient civilizations did not merely observe the sky, they synchronized with it, tracking patterns, cycles, and celestial rhythms that repeated with remarkable precision. Indian astronomical treatises like the Surya Siddhanta encoded cyclical time, planetary motion, and angular circulation with striking accuracy, forming one of the earliest structured frameworks to interpret the celestial mechanics. The division of the sky into nakshatras and rasis were not just cultural, it was a coordinate system mapping celestial positions relative to Earth with a repeatable and observable reference model. What is often overlooked is this. These systems implicitly recognized periodicity, resonance, and gravitational influence even without formal laws or mathematical expressions to define them. Birth charts were, in essence, time-stamped cosmic snapshots, primitive space-time tagging that attempted to correlate cosmic positions with the moment of biological emergence. While modern science rejects deterministic astrology, the underlying framework reflects an early attempt to correlate cosmic mechanics with biological systems. Simultaneously, mathematicians like Aryabhatta and Brahmagupta introduced zero, nonlinear equations and trigonometric identities, foundational mathematical tools that would later become indispensable in orbital mechanics and trajectory calculations. Space exploration was mathematically possible centuries before it became technologically feasible. The invention of telescopes transformed the sky from abstraction into measurable reality. Early refracting telescope systems using lenses to bend light enabled the first magnified planetary observations, while reflecting telescope designs using mirrors eliminated chromatic distortions and extended visibility deeper into space. When Galileo Galilei observed Jupiter's moons, it shattered the geocentric model by proving that not everything revolved around Earth. Soon after, Johannes Kepler described orbital mechanics. Through precise mathematical laws of planetary motion, and Isaac Newton unified motion through Newtonian mechanics, linking force, mass, and acceleration under universal laws. Gravity, once understood, became quantifiable and predictable. And once something becomes quantifiable, it becomes negotiable. Escape velocity emerged as the first gateway beyond Earth, a defined speed at which an object can overcome gravitational pull without further propulsion. The 19th century quietly built the blueprint of spaceflight. Konstantin Tsiolkovsky formulated the rocket equation, revealing that propulsion is fundamentally constrained by fuel mass fractions where most of the rocket's mass must be propellant to achieve escape velocity. At the same time, the spectroscope unlocked stellar chemistry by analyzing light spectra, proving that hydrogen, carbon, and oxygen, the building blocks of life, exist universally across stars and galaxies. This era answered a profound question. We can reach space and life's ingredients are already there. Modern rocketry did not emerge from peace, but from conflict. Robert H. Goddard introduced liquid fuel engine, enabling sustained and controllable thrust through regulated combustion, far more efficient than solid propulsion. The V-2 rocket, developed under Wernher von Braun, became the first human object to reach the edge of space. Its true breakthrough lay in systems like the gyroscopic guidance system, which stabilized orientation during flight, and aerodynamic control fins, which maintained directional stability through atmospheric ascent, transforming rockets into navigable missions rather than uncontrolled projectiles. With Sputnik 1, humanity crossed a psychological threshold. We were no longer earthbound, we had placed an artificial object into orbit. Soon after, Yuri Gagarin proved that humans could survive in orbit under microgravity conditions. The pinnacle came with the Apollo 11 moon landing, powered by Saturn V, a mission so powerful it redefined what engineering could achieve through scale, precision, and reliability. But Apollo was not just about propulsion, it was about integration. Multi-stage rockets shedding structural mass mid-flight to improve efficiency, guidance computers performing real-time navigation calculations, heat shields using ablative materials to survive atmospheric re-entry temperatures exceeding thousands of degrees. Space exploration became a convergence of disciplines, not just a rocket problem. Space evolved from a destination into an infrastructure. Stations like Mir and the International Space Stations enabled long duration human presence in microgravity environments, powered continuously by solar panels converting sunlight into electrical energy. The Space Shuttle introduced partial reusability, while docking mechanism allowed precise alignment and connection of spacecraft in orbit, enabling modular construction. Geostationary satellites, positioned at fixed altitudes relative to Earth's rotation, turned orbit into an invisible backbone of communication, navigation, and Earth observation system. And the organizations like ISRO proved that precision engineering, cost optimization, and mission efficiency could make space accessible beyond traditional superpowers. The 21st century is not about discovery, it's about optimization. Rockets like Falcon 9 introduced reusable boosters capable of controlled descent and vertical landing, dramatically reducing launch costs and turnaround time. India's PSLV became a symbol of reliability through consistent mission success, while GSLV advanced cryogenic propulsion using supercooled liquid hydrogen and oxygen for higher efficiency and heavier payload capacities. Autonomous systems like the Perseverance rover began making decisions on distant planets, powered by artificial intelligence capable of terrain analysis, obstacle avoidance, and scientific prioritization without real time human input. Exploration was no longer limited by human presence. We are now entering the most transformative phase of space exploration, where propulsion, sustainability, and global collaboration converge into a unified progression. At the center of this transition is the Artemis 2 mission, launched aboard the Space Launch System carrying the Orion spacecraft. For the first time since Apollo, humans are being sent beyond low Earth orbit again into deep space environments. A lunar flyby mission, testing deep space navigation, life support systems, communication delays, and high speed atmospheric re entry under extreme thermal conditions. Not just a mission, but a validation of human capability in deep space operations. It prepares the path for Artemis 3, aiming to land humans on the moon again, and Artemis 4, focusing on building a sustainable lunar orbital and surface infrastructure. At the same time, the world is moving forward together, yet independently. The United States, through NASA, is building a long term lunar ecosystem under the Artemis program, designed as a stepping stone toward Mars exploration. India, through ISRO, is preparing for Gaganyaan, its first indigenous human spaceflight program, developing life support, crew escape, and orbital habitation systems. China is advancing with Chang'e 7, a complex multi-component mission involving an orbiter, lander, rover, and hopping probe to explore lunar polar regions and detect water ice deposits. Europe's ESA is mapping the dark universe through the Euclid mission, studying dark matter and dark energy by observing large-scale cosmic structures. Japan's JAXA is pushing forward with advanced robotic missions and Mars exploration initiatives, focusing on precision landing, sample return, and autonomous systems. These are not isolated efforts, they are multinodal expansion of human civilization into space. Alongside the missions, new technologies are redefining what is possible. Ion thrusters generating thrust by accelerating charged particles, enabling ultra efficient propulsion over long duration with minimal fuel consumption. Nuclear thermal propulsion using nuclear reactors to heat propellants, potentially doubling or tripling propulsion efficiency for faster interplanetary travel. In situ resource utilization, extracting and processing local materials to produce fuel, oxygen, and water directly on the extraterrestrial surfaces. Space based 3D printing using additive manufacturing to construct habitats, tools, and structured components directly in space environments. Space solar power, capturing continuous solar energy in orbit and transmitting it wirelessly to Earth or other space based systems. A subtle but powerful shift is happening. We are no longer preparing to visit space, we are preparing to live and operate with it. Yet, there are limits. Radiation exposure from cosmic rays, microgravity induced muscle and bone degradation, psychological strain from long duration isolation, and fundamental speed limits imposed by relativity. Even with advanced technology, the human body remains constrained. The human expansion is not limited by missions, it is limited by biology. Organic molecules, amino acids, nucleobases have already been detected in meteorites and interstellar clouds, the building blocks of life. are not unique to Earth. Life may not be rare, it may be inevitable, wherever the right chemical conditions exist, but it may not look like us. It could exist in unfamiliar biochemical forms or even entirely different modes of consciousness and organization, because consciousness itself may not be limited to what we currently recognize or understand. Interstellar travel remains impractical, at least for now. With our current level of understanding science, even reaching the closest Earth-like planet, the Proxima Centauri, which is 4.24 light years away, with the most advanced spacecraft, Voyager 1 or New Horizon, will take us 80,000 years to reach. Yet, there are theories that have already sparked debates centered in making such planets human habitable. That is one of the most interesting space topics that are not discussed often. We already have a way with it. If you are really interested, comment voyage and we'll get ourselves deployed in discussing that. Simply put, the future becomes strategic. Layered expansion, moon, Mars, asteroids, orbital habitats, each acting as stepping stones in a larger system. Not searching for Earth-like worlds, but creating them, terraforming synthetic biology, controlled ecosystem capable of initiating life-supporting conditions from microbial beginning to the complex living systems over time. At its core, space exploration is not about rockets or planets. It is about continuity of intelligence. We are the result of billions of years of chemical evolution, and the same chemistry exists across the universe. The universe is not just a place, it is a process that produces awareness here and elsewhere. If that is true, then humanity carries a responsibility to remain united, to represent Earth as one civilization, not using technology against its own self, but to establish life forms further, to expand not with destruction but with design. Earth is our origin mode. Space is our next medium of existence. From ancient skywatchers to missions like Artemis, one truth becomes clear. We are not separate from the universe. We are its intelligent evolution of exploring itself. Stand not as spectators of the cosmos, but the conscious participants in its evolution, where every idea you build, every system you design, and every sustainable step you take becomes a continuation of the universe, thinking, creating, and advancing through you. Let's establish habitability in Earth and beyond. Let's innovate to sustain. Don't forget your formalities. To your channel, Nandri Vanakkam.